Hi, everyone. Thank you for joining us in this late afternoon. Hope everyone got their coffees. So today we're going to talk about massively scalable storage. We're going to talk about containers and how Azure Storage really works well integrated with containers. My name is Vaibhava Ramadas. I'm a product manager at the Azure Storage team in Microsoft. And with me is Malcolm, who is a principal engineer as well. So thank you for joining us, and we'll get started. So on the agenda for today, we're going to kind of start a little bit to introduce you to, what are the challenges that users see when trying to leverage and use stateful workloads in the context of container-based applications. We'll do a quick overview of the Azure Container Storage service and then sort of do a deep dive and talk about the architecture and how it's built on the platform. And we will then take an example of a backing storage, which is the Azure Elastic SAN, and talk about how we built SAN to really scale and work with containers. So that's on the agenda for today. So just to kind of set some background and context, over the last few years, we've really seen an increase in the number of stateful container workloads that are running on the platform. This could be anything from sort of a roll your own database, so users running Postgres or MySQL, or an AI/ML application, so say Jupyter Labs or Kubeflow. And all of these applications need and use state. And so that state typically is stored on a backing storage, which is basically a form of persistent storage on the platform. And so as we see the number of these applications and workloads increase on the platform, some of the challenges that we started to notice is that it is actually quite hard to leverage sort of the existing inherent options when you're running container-based applications. So this is kind of across different cloud platforms. If you look at the offerings that are in place today, really you'll notice that a lot of those were built for IaaS kind of workloads or infrastructure as a service workloads, and they don't work as well in the context of containers. And users find this super challenging. And some examples of places where this doesn't really align or work well is, when you're looking to sort of deploy containers and scale them really fast, or if you're looking to leverage sort of native Kubernetes behavior where, it fails over and ensures application availability, but the storage doesn't really respond well to that. And so as we sort of view these challenges, we are looking at ways in which we can improve the platform to better serve users who are running these stateful workloads. Now, just a quick overview of the Azure Container Storage service. This is in preview on the platform. And what this really enables is a abstracted way for you to leverage different backing storage on the platform. So whether this is Azure Disk or local NVMe, and really expose that through the Azure Container Storage service as persistent volumes for any stateful pods that may be running in Kubernetes or other container platforms. So the key callouts here is that this service really enables a Kubernetes native or container-centric experience. So as a Kubernetes user, you're really looking to use sort of the existing control plane, and you're able to do all of the lifecycle management of the storage in the context of the Kubernetes control plane, but you're also able to get all of the benefits of container scale. So the ability to deploy and scale out really fast, as well as a unified experience around different backing storage options. So kind of digging a little bit deeper into this, what we've really enabled here is there's like 3 parts here, as you see. One is on the storage pool side, we have the ability to sort of bring together different storage resources as a single entity that gets integrated and exposed to the Kubernetes cluster through Azure Container Storage. We have sort of the service itself, which provides data services. So depending on what is available in the backing storage, Azure Container Storage will add on different data services, so think like snapshots, replication, and so on. And we have sort of the protocol layer, which then exposes those volumes that are served through the service onto any stateful pods or any applications that are running inside the Kubernetes cluster. So those are kind of the 3 different layers of the application. And so as a user of this, So if you are looking to run and deploy applications on containers or Kubernetes and really want to be able to scale out your application and use persistent storage as part of that, you're either kind of playing the role of an operator, so someone who's like sort of deploying the cluster and managing the storage environment, or a developer, right, who's basically deploying and running these applications. And so as an operator, we've sort of really simplified this experience, so for you to just create these storage pools and be able to provide a backend storage that you can use as part of the pool. And then as a developer, your experience should be exactly what you expect today when you deploy and use Kubernetes, which is basically being able to use persistent volumes as part of your application. So if you run a stateful set or other kind of any stateful pods or deployments, you can basically use PVs and PVCs as you would today. Now, this is a lot of Kubernetes-specific jargon, so if you're not familiar with this, don't worry. In general, the key call-out here is that the service enables users to leverage this, the underlying storage systems in kind of what they would expect as a native way to leverage and scale storage. Quick example on this, so in terms of the operator, for some YAML enthusiasts, you basically will define something very simple. So what's my backing store, and then what is the actual capacity that I want to specify. And then from a developer perspective, if you're deploying a stateful set, you're leveraging and specifying whatever storage class that is in place. So in this case, the AZ Store Azure Disk Storage class, which is served from this storage pool. So that's how you would sort of use it and leverage it as part of your application. Now, let's get into a little bit of a deep dive and actually look at what are the components that's behind this that serve this up. And so if you look here, there's a few different layers in place. So starting with sort of the protocol layer that's exposing volumes using remote protocol, to the data services layer that's really adding on any additional data services that the backing storage may not have. So this could be like snapshots, replication, and such, as well as the sort of capacity provisioner, which manages those storage pools that we talked about that could deploy and run on any of these backing storages. So the storage pool construct really enables a neat abstraction layer so that it enables different kind of backing storage options to plug in to this architectural model. The key call out here is that we have enabled this with today in preview with local NVMe, our remote disk, which is the Azure Disk, and Azure Elastic SAN, which we'll kind of cover in a lot more detail today. But there is definitely extensibility in place that can enable other backing storages also to plug in here. And we'll talk a little bit more about that in just a second. So just going a little bit deeper into each of these layers, on the data services layer, as we talked about, we really layer on or enable things like snapshots as well as replication. The snapshots here, we've built it so it is native and works well with the container native storage interface, which is the CSI interface. And so we align with the CSI specification and also provide kind of what you would expect in general in the context of snapshots. So the ability to create and scale snapshots, so create snapshots, instantly read snapshots, and then be able to restore from those snapshots for any volumes that you want to restore onto the storage pool and the cluster. And then from a replication standpoint, for any applications that don't replicate, so if you're running, for example, Cassandra, and you're going to be replicating at the application level, you don't need this. But if you're running an application that doesn't natively sort of replicate, you can use the storage pool replication mechanism, and then we in the underlying engine will replicate for you. And so this enables higher availability as well as the ability to sort of get better application integration and availability with sort of Kubernetes, which typically uses those availability constructs to fail over your applications across a cluster. And along with replication, we obviously do additional things like ensure that there's like data consistency and integrity and such, so that you kind of expect that from the underlying engine. On the capacity provisioner, a couple of quick callouts is we use storage pools as a way to sort of aggregate homogeneous capacity, homogeneous storage onto the Kubernetes cluster. So for example, if this is a bunch of local SSDs or local NVMe or Azure disk, this gets sort of grouped together and exposed into the Kubernetes cluster. And from a user standpoint, it really simplifies things. So I, as a user, can say, hey, my application needs this much capacity and these many IOPS. And then the Azure Container Storage service will ensure that you get the right data from the appropriate pool, and that gets served into the application. What we also do as part of the capacity provisioner is understand this notion of zones. And so within Azure, we have multiple zones within a particular region. And so the service will understand the different zones and ensure that, for example, your placement of storage is in the context of the correct zone so that you can actually use it in the context of your application pods. The key thing also here is that we offer the ability for you to have abstraction so that different kind of backing storages can work with our Azure Container Storage service. And that's sort of represented here. And so this is an example of different kind of backing stores. So if you're wanting to leverage local SSDs or NVMe, we will layer on all of the different data services components on top of that. If you are bringing in a remote disk that may have some of these things already built in, like encryption or replication, and we will basically just layer on whatever components are needed to serve this to the container storage layer, which is basically the thin provisioning and the protocol, remote protocol for mounting. And then if you are, say, bringing in a SAN, which has a lot of the storage management and data services components already built in, then we kind of simplify this for you and just sort of expose volumes. And the key call out here is the platform is built to be extensible. And so, kind of call out here is, if you have a storage capability and you offer it today and you believe that this could be interesting for you to plug into as a backing storage, please let us know. And this is something that we'd love to kind of chat with you about after the session. The other call out here is Azure Container Storage is built in a way that it will be deployable on Azure Edge as well in the future. And so from an edge perspective as well, if you believe that this will enable you to plug in as a storage offering, then please let us know. All right, with that, I'm going to hand over to Malcolm, who's going to talk to us about Azure Elastic SAN.
Okay, thank you. So here we've been describing before a bit about where Elastic SAN fits into the container architecture. We are one of many different backing stores underneath containers. The real question, though, you should be asking is, you're talking about containers and SAN. Like, that's a really odd combination. Now, the question I'd throw out to you, though, is what is a SAN? And I know you've all worked with SANs. You all know the answer to that. But if you distill it down into the attributes that it's offering, what happens is somebody buys an appliance that has a pile of disks and it can do a pile of IOPS. And you can shift the workload to any workload. It doesn't care. Those IOPS, that capacity can't be used by anyone else. It's completely reserved for them. That has good and bad attributes. So okay, we're a cloud. Surely that's the same, right? The challenge we've got as a cloud is really a bit of a business model thing. We have all of these nodes, but for us to offer a good financial business, we need to keep those nodes relatively well utilized. Now this is a different semantic to an on-premise SAN. On-premise SANs are frequently very idle. But when we have high utilization, what this means is load shifting is a problem. If load disappears from one server and pops up on another server, the first thing that'll happen is we will experience degraded latency, right? Because that server is overloaded. The second thing is we will realize there's a problem and we will start moving things. And there will still be degraded latency. And then we recover. Now, if you put that with a workload like containers where things are starting and stopping all the time, what happens is you're running in that degraded mode way too often. So when we looked at this problem, what we were really asking is how can we avoid that? How can we get to a point where the degradation is massively reduced? So I'm an engineer, I'm a developer, I love to talk about how things work. Unfortunately, I've been told that I need to tell you what it is before I can tell you how it works. So what is a SAN? Well, we're selling an appliance, it has a bunch of storage and IOPS. You can go to the portal and say, I want one, and you access it through iSCSI, and it's trying to be as familiar as possible to an on-premise SAN experience. What it's not, though, it is not a reserved appliance. We're still running on shared hardware. So then the question is still, how do we achieve high utilization, shared hardware, while offering these IOPS reserving semantics? So we've really got a 3-level hierarchy in terms of administration and resources. The first is you get a SAN, which is a typically large appliance. So we were thinking in the order of 64 terabytes as a minimum unit of size. For containers, we've scaled that down quite a bit. But a SAN has a base provision size, which comes with a certain number of IOPS. You can add more capacity to it if you want. That's what we're calling capacity only. But there's no additional IOPS there. So you're buying a pile of IOPS. Within that is a volume group. A volume group is a unit of administration. You set security policies or other configuration options that you want to apply to a series of volumes. But really all it is a unit of administration. Finally, at the data layer, you have a volume. You might consider it a LUN. It's an endpoint that you can connect to via iSCSI. There's a pile of blocks you can read and write. So this is the area that I think we'll focus on a little bit more. So I mentioned this before, but for container storage, we're looking at these very small SANs. So the idea is you have a pool of storage. Containers have individual volumes. We can create and delete volumes. We can attach to volumes quickly. And the IOPS can shift to wherever the container happens to be. Okay, now we can talk about how it works. Great. So Azure Storage, this is not new information. This is all published in a paper. We have a 3-layer architecture. There is a front-end layer, which is where requests arrive. There is a partition layer, which owns metadata and distributes them in a reliable fashion. And there is a stream layer, which is an append-only data store that is replicated. The key thing that I want to focus on here is about what these layers do. So we have a front-end layer that implements protocols. And as you'll see, we're adding a new protocol, so there's some changes there. The partition layer is where we own metadata. That's the area I work on, therefore it's the most interesting. And what we've done there is we traditionally had a key value store, and the way we partition it is we chop up individual key ranges and we hand them out to different servers. So we call those units partitions. Every server might have a dozen, 100 partitions, and those are units of load balancing. We can move them around, we can split them up, it's just a key range, right? The stream layer, we haven't really changed as part of this project. We still need all of the same resiliency and availability semantics. So now if we drill into that front-end layer, even within that front-end layer, it's a single role running on a single server, but it has different components to it. So at the top, we've got a protocol layer. And underneath that, we have a service layer. There's actually a couple others. But the protocol layer is the thing that is implementing the externally facing protocol. We're trying to keep this as thin as possible because customers come to us all the time and say, hey, we want more protocols, so we want to make adding these really cheap. Separating the data representation, so basically the client layer that talks to the metadata system from the protocol, enables us to expose different storage representations with different protocols. And we rely on that. So today, we have an iSCSI front end as part of SAN, but internally, we're still using HTTP and REST for snapshots and migration, replication, import, export. We use it extensively. So we really want to be able to switch between these protocol front ends easily. So using iSCSI as a network endpoint means every individual client is establishing TCP connections. The way Azure works, every cluster has a single IP address that's externally exposed. So if you connect to it multiple times, we will send those requests to different servers. So if you use an MPIO configuration where there's multiple underlying connections, those are all going to different backend servers. So this enables you to scale out and eliminate TCP bottlenecks, but it's also eliminating backend bottlenecks. Now, I want to say, particularly since it's the afternoon and you're all falling asleep, but you're all also storage people, we're supporting MPIO. It gives us performance. It's ubiquitous. Everyone has it. But I was thinking about words to describe MPIO, and I came up with venerable. You have to respect it. You have to respect it. But it's a total hack, right? The way MPIO works, if you haven't looked at it, is a device is surfaced, and the kernel sees multiple devices. And then it queries the serial number, and then it says, you know, those are really the same device. So what I'm going to do, I'm going to hide them, just expose one, and implement some scheduling policy across them. The problem I have as someone who works on a backend is I can't tell the difference between a well-configured and a poorly configured system. If a single system mounts the same disk twice, two things are going to happen. One, they've set it up correctly and they're going to get great performance. The other is they've set it up wrong and they're going to end up with incoherent caches, last writer wins, and catastrophic data loss. Can't tell you which is going to happen. So the challenge I have for everyone who's thinking about these issues is MPIO is great, we need it, can we do better? So we were doing iSCSI. Why are we doing iSCSI? Partly because we're not very cool, that's true. But it also gives us fantastic support across different initiators. So Linux has a huge range of protocol support. We're Microsoft, we care about Windows a little more than a lot of others do. Not mentioned on this slide, Elastic SAN also built for VMware. We have VMware running in our data center. It needs to talk to Azure Storage. Makes sense to use industry standard protocols. There's a lot of advantages there. Now, as someone who's involved in this, VMware has presented some interesting challenges. So in 2023, I built SCSI 2 reservations, not SCSI 3 persistent reservations, SCSI 2 reservations. Anyone else working on SCSI 2 reservations in 2023? Anyone? No. Good. That's fantastic. Okay, so one of the things we gain, particularly for containers with iSCSI, is we're not limited by the SCSI bus. If you attach things as SCSI disks under a VM, that VM still has to see them as devices in terms of SCSI. With iSCSI, everything's a network connection. You can have far more. You're not limited by that. And when you look at container workloads where there's a lot of pods running on one physical server, eliminating that limit makes a lot of sense. Now, of course, we're looking at other protocols. No surprise there. Part of the motivation is encryption. So if you haven't looked at iSCSI recently, iSCSI's specification says if you want encryption, use IPsec. Now think about that in terms of containers. Do you really want every container to have its own IPsec tunnel? So currently, we don't have any encryption story, which is unfortunate. Now NVMe said, you know what, we'll do TLS, PSK. And if they stopped halfway through, that would have been great. But they didn't. They had to finish and say PSK. Now, if you didn't go to Claudio's talk on NVMe encryption and security, I highly recommend it. Go watch the recording. He covered a lot of this. But my complaint here, complaint, whatever, is that PSK is very difficult for everyone to work with. Because you've got to provision a pre-shared key on both sides. And in the current security landscape, you have to consider things like key rotation, which is not really defined. And NVMe doesn't provide even mechanisms to describe those keys. So as a security mechanism, there's real questions, even now, before we've built it, to say, well, does this even meet the bar for security today? Which is very frustrating. And to put that in context, in Azure Storage, the way we locate a storage device is through DNS. So in Claudio's talk, he was saying, part of why we got to PSK is because storage adapters don't use DNS and certificates are issued based on DNS. So there's a mismatch. We can't use X509 certificates for encryption. Well, in our system, we totally can. As a matter of technology, it would be very straightforward. We can't because there's no standards support and we wouldn't have any other implementation to integrate with. So if anyone is thinking about certificates in NVMe, I would be glad to talk to you, and hopefully we can make something work together. So how do we scale containers? Well, this is where we have network connections, which are fast to set up and terminate. In our system, authentication is a little interesting too. Networking in Azure, packets are tunneled, right? So if you make a connection from a VM, We will wrap that up and then send it around our internal network. The advantage of this tunneling is we know where that packet came from. We know which customer it originated from. So we're not doing any explicit authentication here. When we receive that TCP connection, we know who it is from. And so that accelerates this attach time. Obviously, it is simpler if you have a pool of containers, you're running those together, you want a pool of storage, you can administer those together. And of course, we can scale IOPS and capacity based on demand. The real underlying assumption here is that individual load among containers will change. The collective load is much more stable. So what did we do? We did sharding. Now, I stressed before that our metadata store is a key value store that partitions based on key ranges. Why did I say that? Well, because the way we name our shards here is built on a hash. So when you have a hash function, we now have a random distribution. We take a volume, chop it up into pieces, randomly distribute it. If load shifts from one volume to another, in theory, we are moving from a large number of randomly selected backend nodes to another large number of randomly selected backend nodes. Assuming randomization works well, the load isn't really shifting across servers. So that's how we implement this semantic that we were really looking for. You can have many containers, load is shifting, and it's not creating load balancing. But of course, with sharding, we have many other challenges about how do you keep a volume coherent. Well, here we're cheating because we've got a single network front end. Except, as I said before, we don't have a single network front end because we have MPIO. So we have many network front ends. So what do? You can have one connection if you want to a large number of volumes in SAN, or you can have many connections to the same volume. Just depends on your workload, what works for you. But the problem we've got is now you've got multiple of these connections. How do we keep volume-wide state coherent? And what we've done here is coordinated across the front-end nodes. And that happens because, well, a couple of reasons. One is there's a lot fewer of them. When we've sharded the data, we've got a huge number of shards containing actual data, but we have maybe a dozen front-end nodes. So coordinating among the front ends is just a smaller number. There's another really key reason here, though. The metadata partitions have to be durable. If you have a metadata engine that owns a key range, that can fail over to a different node at any time. So if we've made a state transition related to taking a snapshot or something like that, we need to persist that somewhere to handle that potential failover. Front ends are different. You've got a TCP connection to some node. If that node crashes, great, it's consistent. It's dead, but it's consistent. So we don't have the same durability requirements. We just need to reach out to the front ends and say, hey, we're doing this state transition. Stop what you're doing. We'll get back to you. If anything goes wrong, good, right? We're good. So here, for shard creation and deletion, I said before we have a hash function, and then we're sending this thing out as a named entity to some partition server. We create these shards on demand. So that is another cute trick we did where you can have a very large volume. There's not a lot of metadata behind it. We're creating as much metadata as you need. The problem with creating it on demand is we're doing it in response to writes. You don't want two round trips to say, okay, the user is writing to some LBA, let's poll and check if this object exists, right? That's going to suck. You also don't want to have a write message that says, by the way, here's the user's data, and here's a pile of extra state about creating that shard if it didn't exist before. So we did a compromise thing. We send the write with a single bit that says create if it's not there. And that partition server, if it doesn't exist, can query the state from the volume. So it's making a cross-partition call, which is a little unnatural, but it gives us the properties we want. We're keeping write cheap. We're sparsely populating shards. And it gives us that efficiency. Now, deletion in distributed systems is also interesting. I messed it up the first time. Don't make my mistake. Normally distributed systems work by achieving consensus, but you can't achieve consensus when you're trying to delete something, right? Because the act of deleting it is destroying the consensus. So the way we did deletion here is through background scans. Periodically, every shard will check with the volume and say, Are we still good? And based on that, it can mark itself a deletion, or it can continue to exist. We're actually doing similar things there for snapshots and other scans. We retain all data for a period of time, so if we've made a decision that the data needs to die, we will mark it and say, okay, don't delete it for a period of time in case we need to recover it. But nonetheless, it is all driven completely asynchronously. So as part of scaling even further, the normal way we place things is we create a series of disks on a single storage tenant. And a storage tenant in our world is a couple of hundred machines, give or take. So we can place different volumes on different tenants. Now, I'm kind of torn and conflicted by this, just to be clear. I said before we were doing all of the hash-based partitioning, random placement, so that load can shift, because it's on the same nodes. Well, here it's not on the same nodes anymore. The hope here is that if you have a large enough workload where we're spreading you across 2 clusters, you're not going to shift all of your load from one cluster to the next cluster in one go. You will have different containers starting and stopping, and those things will also be randomly spread across those clusters. So although it's not strictly the same nodes, the hope is we can still achieve decent distribution. So we have scaling there by multiple storage tenants. We have physical storage of metadata across a large number of servers. We have replicated data that is spread across large numbers of servers. So the result is millions of IOPS, lots and lots of throughput. Latency is not quite what we want it to be. We'll work on that. But nonetheless, we can at least scale out very, very well. Okay, so thank you. If you have any questions, you can ask us now, or reach out to us later, or grab us when we're around. We'll be here for a while.
Please. Go.
Workload balancing, are you doing anything for 2 additional type of workloads? One is if there is a missing node and you're regenerating the data, as well as any background data health check. Is that creating additional workload?
So the question is, do we have additional workload based on bringing up new copies of data or scrubbing existing data? And I think the answer is yes, but it's transparent to this application, because that is really handled by the stream layer, which we didn't touch. So the way our system is working, we're issuing appends to a stream layer which replicates 3 ways. If a node hosting that data dies, we now have 2 copies, and there will be a process to bring up a 3rd copy of that data. We periodically scrub it, we check CRCs for health. But that's handled at the layer that we didn't touch. I think, is there hardware load generated? Yes. We haven't made it any worse, right? The amount of data is the same. I guess one thing I didn't comment on, all of our metadata is stored on that same stream layer. So that's how all of our partitions can move, is we're just loading, metadata from a distributed store. So the scrubbing process that we're doing applies equally. Now, we still have the same number of ranges, whether it's in one disk or whether we've chopped it up into many. So we haven't changed that at all.
Go ahead.
Yeah, question. One, what are you doing for AWS?
Sure.
And the other, multi-zone, one of the issues coming up is talking between the zone and slower and usually more expensive. So how are you trying to optimize it?
Yeah.
Investment?
Absolutely. So I'll repeat the question. So the first question was, what are you doing for RWX or read-write many workloads or read-write many storage? And then the second is, in terms of multiple zones, how do you ensure that, do you have traffic that's going across zones? How do you sort of optimize that? So the first sort of call out on the read-write many piece is that, the preview of the service right now only offers read-write once, so it's different backing stores, but it's only read-write once. We are looking to expand that out, and so that's something that we're looking into. So we don't have that yet, so just call that out. And then the second piece on the multi-zone clusters is, using AKS or Azure Kubernetes Service and deploying in a multi-zone manner is actually super, super common. Everybody, there's a lot of users that do that today. And so what we do with Azure Kubernetes Service, Azure Container Service is that we ensure that you actually have multiple zones as part of a storage pool, and we enable you to zone align. So it kind of, you can think of it two ways. If your application has application level replication, then you want zone alignment and selection, right? So that your pods can be in different zones, and then your application can sort of replicate and handle the availability. If your application doesn't do that and you want zone redundancy as part of the setup, then we will sort of enable that with our zone redundancy model as well. And so we'll kind of support both depending on what kind of your application expects.
Yeah, in case of the second one, that you want locality for reads. You want to make sure the reads don't cross zones. Do you have any mechanism?
Yeah, so our zone redundant storage inherently has a model one where we replicate everywhere for availability, and we do have certain optimizations in place that will help sort of provide you the best performance. But in general, I think that typically applications that use the zone replicated model have in some ways a higher expectation of availability than perf. And so there's always a trade-off, right, between availability and perf. And so generally the applications that use ZRS are more like kind of inclined around availability. That's kind of what we see. Thank you. Go ahead.
You mentioned that you have multiple backends in addition to Elastic SAN, and that you have NVMe over fabrics. Can you maybe expand on that? Which backends use NVMe over fabric and which transport you use?
So,
I'll take the first part of that question and then, okay, so the question was, we said that we support different backing stores with Azure Container Storage, and so what are the different backing stores that you use, and how does NVMe over Fabric plug into this? So in terms of the backing storages, today we offer 3, which is all a part of Azure platform today. So one is the local NVMe, that's a part of the compute nodes. And then Azure Disk, which is kind of our remote disk offering. And then Azure Elastic SAN. So there's 3 different backing storages that we offer today, but it is extensible as we called out. The NVMe over Fabric piece is more of the protocol layer. So it's more about when the volumes are created and managed, how the volume itself gets exposed and mounted to the pods. And so that's sort of where the NVMe over Fabric piece comes in. But I'm not sure.
yeah, so we in Elastic SAN don't have NVMe OF today. I mean, obviously we're looking at it, and we're looking at what we can do to have broad adoption. We went with iSCSI first just because the number of initiators that supported it. And now the challenge when we're looking at NVMe is, 1.1 or 2, and what are the consequences of those choices? But we're definitely looking at it.
So, just to double check I understand, do you use today, for example, NVMe over TCP or NVMe over RDMA to connect the pods with Azure Managed Disk somehow, or we direct attach building some NVMe over Fabric target on top of a specific server?
So I'll take that. So the question is, today, how do you expose Azure disks into the containers in AKS? Does it use NVMe over RDMA or something else? So today, what we have on the platform is we have a sort of inbuilt CSI driver, and what we do is we mount the Azure disk to the cluster node. Using SCSI protocol, which is sort of what we have on the platform, and that is then sort of mounted into the container. So there isn't sort of a remote access protocol in place. It's really exposed from within the cluster node, and it can be mounted on as a ext4 or XFS.
So there is no NVMe over Fabric?
Not with the Azure disk existing model. With Azure Container Storage, we do mount it using NVMe over Fabric.
Okay, so Azure Container Storage is a local NVMe, and you create a target immediately pod and create. So I still don't understand which use case is NVMe over Fabric. Sorry. I understand Elastic SAN does not use this size class. I understand Azure Managed These do not use because they're exposed as local NVMe device. The third option is the direct attach local NVMe. Correct?
Sure.
So where is the NVMe over Fabric?
So, okay, so I will maybe go back a few slides, which may help illustrate. Sorry, we had a lot of slides. Almost there. Okay, so if you look at kind of the model that's there historically, and it's fairly common in other platforms as well, the underlying device is direct mounted onto a cluster node and is directly exposed to a pod, right? What Azure Container Storage does is it provides thin provision volumes, and those thin provision volumes are then mountable using NVMe over Fabric.
So Azure Container Storage behaves as an NVMe over Fabric target, and it's running on dedicated virtual machines, where it's running the Azure Container Storage.
The Azure Container Storage piece itself runs inside of the cluster.
As part of the AKS cluster.
Yes.
Same close. So why it needs to expose NVMe over Fabric to persistent volumes if they're local? Or I'm missing something?
No. So in the model where you have the disk directly mounted, it is like a single device, right? Like a LUN on like the node itself, right? Which is a direct one-to-one mapping with the volume. Versus in case of a thin provision volume, you need that to be accessible somehow, right? It isn't exposed as a local device at that point because it's a thin provision volume. Yeah, sure.
Maybe what will help you to understand, is this based on OpenEBS?
So if you look at the overall thin provision volume model that exists and also volume orchestration, the community has been working on this for a while, if you think about it. There's lots of different ways in which this is done today, if you look at different projects that are out there. In case of Azure Container Storage, we are derived in some ways and we match a lot of the community-based standards. And so that's kind of what I will say. Go ahead.
For someone who is not familiar with Kubernetes and containers at all, like in the beginning you said about stateful container applications or something like. How did that statefulness affect what you do to the storage? Because in my mind, kind of shouldn't matter because the storage is by definition stateful. You write data and it has to be there for later retrieval. So like, why did statefulness matter? That's my question.
Because Kubernetes was created for non-stateful application, and then later they added the persistent volume for stateful application, where special Kubernetes components are related to that.
Okay, I'll repeat the question. Thank you for taking it. So the question was, hey, we talked about stateful workloads. Why does it matter in the context of how we think about Kubernetes or storage? And so the key thing is that when you're running a stateless application, obviously you're not talking to storage, so you don't need anything. If you are having any state that your application needs and needs to read and write, there's some different options, right? So one option is you use some sort of ephemeral data. So you just use like a cache, right? You use that data and then it's done, and your application like may restart or whatever, and you don't actually need that data. So we're okay. Alternatively, if you are running a application that needs to store data, so typically that could be anything. It could be like you're rolling your own database, you're doing like a Kafka Elasticsearch, whatever. You need an underlying set of base storage that you're working off of, as well as you are going to be reading and writing to that you need some mechanism to be able to access and use that storage, right? Now, this is done today, right? Obviously, there's different ways in which people use the different existing sort of storage systems to do that. The key call-out that we had at the beginning of the presentation is that as containers are deployed and scaled, there's a lot of them, in terms of microprocess architecture. And because there's so many of them, we need to make sure that the storage is able to respond and scale effectively with the lifecycle of the container themselves, right? And so the thin provision volumes here enable that mechanism, which is that it allows the ability for you to create lots of these volumes and scale them up very fast, if that makes sense. Yeah, thanks. Any other questions? Yeah, go for it.
What's the Azure Container Storage based on existing storage software or from nothing?
So I think I was just sort of mentioning that previously as well. So the notion of thin provision volumes as well as volume orchestration, it exists in the community, right? So if you're familiar with kind of the different CNCF projects, there's multiple that have done that in the past or continue to do that. And so we definitely sort of wanted to use similar concepts because I think from a Kubernetes user standpoint, we believe that people are familiar with those as well. So in some ways, we use very similar concepts as we built the service out. Any other thoughts, questions? Any takers to talk about encryption on NVMe? NVMe off.
Set key part. It's already there.
So, I think you mentioned that per tenant is about 200 costs. At some point it will max out. Do you have any kind of balancing between the tenants?
Oh yeah, of course. So we do migration all the time. I mean, the big thing, remember, is we need to be able to decommission these things when they get old. So there's always a requirement that any data you store, we need to be able to transparently move it to a different set of nodes. Now, I mentioned briefly before that we're using HTTP in our migration flow because we already had migration flow for other types of data that was using HTTP. It made sense to leverage that. But yeah, absolutely, we do live migration. Okay.
Thank you, guys.